Hello everyone, my name is Richard O'Hegarty. I'm a postdoctoral researcher from University College Dublin. This study is focused on the performance potential of domestic heat pumps in a temperate oceanic climate. Specifically, the calculations were based on an Irish climate. The paper forms part of a larger project called NZEB101, which is investigating the in-use or actual forms of renewable energy technologies. But I suppose before we start figuring out what they actually do in practice, I want to run the numbers on the potential performance of heat pumps, hence this paper. So this is an overview of what the presentation will include. I'm first going to give you an introduction into what a heat pump is and why it's worth investigating. I'll then describe exactly how I estimated the performance and what methodology I used. Finally, I'll outline the findings from the study as well as pointing out why these were important. And I'll also provide some of the measured results we have to date. So, why heat pumps? Well, for a start, buildings account for approximately 40% of the final energy consumption in Europe. I'm sure this figure will be quoted a few times at this conference. In Ireland, 60% of a domestic building's energy requirement is for the provision of space heating. Furthermore, of the 900,000 buildings which have received a building energy performance rating, 88% are not up to cost optimal standard and consume more than 125 kilowatt hour per metre squared per year. In an article published last year, it had been reported that the Irish government planned on installing over 600,000 heat pumps by 2030 to tackle the poor energy forms. So it's clear a solution is required, but are heat pumps the right solution? Firstly, for those who don't know what a heat pump is or does, it essentially extracts thermal energy from a natural source and upgrades that energy to something more useful, using electrical energy. The amount of useful thermal energy you can get out of a heat pump is more than the electricity you put into it. So to evaluate the performance, coefficient of performance is used, or COP for short. This COP is an instantaneous metric of the amount of thermal energy out divided by the amount of electrical energy used for a specific moment in time. Another and more important metric is the seasonal performance, i.e. the amount of thermal energy out of the heat pump divided by the electrical energy input over a specific period of time. So not just at a specific instant. This can be for a day, for a month, and typically for a season. The heating season is typically used between October and April. A number of different factors affect the performance as shown here, and these include the performance curve of the heat pump itself, which is measured following a standard test procedure. So each heat pump would have a performance curve associated with it. The source from which the heat is coming from affects performance. For example, if it's air, if it's the ground, or if it's water. For example, the ground source heat pumps are more efficient because the temperature of the ground is more stable than the air temperature. The distribution temperature also affects the performance, as we'll see in this paper. Whether you're providing heat to underfloor heating system or to old school radiators, that'll affect the output temperature you require and therefore the performance. The climate then obviously affects performance. Colder climates require more energy or more effort from the heat pump. Then the control system has a big impact. For example, what the heat pump's set to do is set to heat a storage tank before. When is it set to turn on? Is it using nighttime energy rates? So all these sort of things affect the performance when you consider it over a year. And then finally, the occupant behaviour affects the performance. For example, if occupants are leaving the window open when the heat pump is on, the heat pump's going to think it has to heat the whole neighbourhood, which will obviously decrease the performance of the heat pump. So how a heat pump performance is estimated is described here in this slide broadly. First, the sample heat pump performance curve is taken as a baseline, and the COP is modelled as a linear piecewise function of temperature difference between outside ambient and heat pump outlet or application temperature. A heating period from the beginning of October to the end of April is assumed, and for simplification it is assumed that the temperature is kept constant for 24 hours. Hourly weather data for Ireland over the past 6 years is used. The energy requirement for heating is based on an energy balance model, assuming a heat loss coefficient of 46 watts per Kelvin, as per NZEB specifications, and a base temperature of 15 degrees Celsius. The SPF is calculated by taking the average hourly COP value over the entire heating period. The results for the SPF for 6 different years and for different outlet temperatures are shown here. Firstly, you can see that the SPFs of 4.5 are possible, but only at very low operational temperatures. For example, with a very efficiently designed underfloor heating system. And you can also see that as the outlet temperature increases to 65 degrees, the COP drops to about 2, for example, for Legionella prevention or for heating domestic hot water. As well as comparing the different operating temperatures for the heat pump, a gas boiler is used as a benchmark and model for the same building. A good efficiency of 90% is assumed in the model. Comparing the primary energy, you can see that a heat pump running at outlet temperatures of 35 degrees consume less than half the amount of primary energy than that of a gas boiler. But at larger operating temperatures, the difference isn't nearly as significant. Over time, it is expected that the primary energy factor will drop down further, as illustrated in the graph on the right, and therefore the benefits of the heat pumps will increase in comparison. Looking at the graphic on the left, you can see that if you had an SPF of 2.1 as a result of an application temperature of 65 degrees, as seen 2 slides ago, the primary energy consumption for that heat pump would be greater than a gas boiler if the primary energy factor is derived above 2.5, i.e. that's where those 2 lines intersect. In terms of carbon emissions, the heat pump again outperforms a gas boiler for all scenarios, although the performance difference is not as great. This is because the carbon emissions from grid electricity is currently greater than the carbon emissions from the natural gas used by the boiler on site. In order to create a bigger gap, the carbon intensity of the grid will need to be improved. It is clear that if this given heat pump is operating at temperatures of about 65 degrees, that the difference in carbon emissions is insignificant. I suppose to sum it all up, this graph shows the ratio between the performance of a gas boiler and heat pump versus the COP of the heat pump for 3 different metrics. It shows that if the COP drops lower than 2.0, the carbon emissions of the heat pump is greater than that of a gas boiler, based on current energy conversion factors. So I suppose the big question is, how do heat pumps actually perform in practice? Do they replicate the performance of the performance curve, or are they something completely different? So it's because we've seen that when they perform with lower COPs, they aren't necessarily as energy and carbon efficient as they can be. How an actual heat pump performs is subject to ongoing research in this particular project. We've installed sensors in a number of different heat pump systems and are collecting data at the moment. This is a snapshot of one of those heat pumps measured for a month. It is an example of the COP versus the outside temperature at 5-minute intervals. I suppose it's clear that the majority of instantaneous COP measurements are between 2.5 and 3.0, which would indicate superior energy and carbon performances, but which are also lower than what is expected. There is also a general trend of increasing COP with increasing outside temperature, which matches the trend of the COP curves shown in earlier slides. So, in conclusion, heat pumps can reduce energy consumption and carbon emissions, and from that standpoint are a worthwhile technology to consider. One thing, however, we do need to be aware of outside the scope of this paper is the embodied energy of the heat pump themselves. We need to ensure that the savings are paid back over a short period of time. We found that the significance of the performance was dependent on the application temperature, the primary energy and carbon intensity of the grid, and the actual performance of the heat pump in practice. Finally, it is important to remember that if the COP drops below 2, the carbon emissions from the heat pump are actually greater than a gas boiler. On that note, I suppose, thank you for listening.